Okay, so the final question for this section, this batch of questions asks us to talk about Dalton's law and Henry's law. So these are kind of the gas laws that are important in respiration when we talk about the lungs. So first we'll start with Dalton's law. So this says that the partial pressure of each gas can be added to find the total pressure. So each partial pressure that is within the lungs or within the body, for that matter, the pressure that can be added together, and each one of those added together equals the total pressure. So we can find ratios of those partial pressures. So in the atmosphere, just generally, we know that our oxygen level is about 21% of our total atmospheric pressure, which is 760. So we see about 160 oxygen in the atmosphere, where carbon dioxide is way less than that. 0.04% times 760 only equals about 0.3 millimeters of mercury for carbon dioxide. So this is different from in the alveoli. What we have is a higher concentration of water in the alveoli. And so what happens there is that our oxygen decreases because it goes into the blood, and our CO2 increases because it diffuses from the blood into the alveoli. So we see our oxygen percentage decrease to about 13.7, which ends up being around 104, but our carbon dioxide increases to about 5.2, which makes our pressure about 40. So these are the ratios of the gases in the alveoli. So the next law that we'll talk about is Henry's law, which is what we use to determine if a gas dissolves in a liquid. So this is the equation that we're talking about here that is Henry's law. It says gas pressure times the solubility coefficient is equal to the concentration of the dissolved gas. So an interesting fact about carbon dioxide is that it is 24 times more soluble in plasma than oxygen. So this is kind of explaining what I was talking about before, that carbon dioxide is much more soluble, and so that will cause this big difference. So if there's an increase in the pressure of oxygen because it dissolves into the blood. So the high pressure of oxygen in the alveoli will cause the gradient will cause diffusion from the alveoli into the blood. It will dissolve into the blood. But the low pressure of carbon dioxide creates a gradient where there will be large amounts of carbon dioxide in the blood, and it will then diffuse into the alveoli and become a gas. So that is where we see the change of those ratios can be explained by Dalton's law and Henry's law. So the next thing that we're going to talk about here is the alveolar gas equation. And so this can be written as the pressure of oxygen in the alveoli is equal to the inhalation of oxygen multiplied by the atmospheric pressure minus the water pressure. And all of that is subtracted by the arterial pressure of CO2 divided by R. And so there are common values that we can use when calculating this. So each of these values have kind of been decided based on normal ranges. And so we know that our inhalation of oxygen is about 21%, like we talked about before, as well as our atmospheric pressure is 760, as well as our partial pressure of water is 47. We know that arterial pressure of carbon dioxide is about 40, like with what we calculated before, and our R value can be represented as 0.85, which is our common value for R. So we use this equation because when we calculate this here, our alveolar pressure of oxygen, and we know how well our alveolus is working compared to the concentration of the oxygen in our blood. When we compare those two, that will help us to know if there's any deficiencies within the gas exchange. If gas exchange is not working properly, then this number and this number will be different. But if everything is working well, then these two things will be the same. And so that is what helps us to know that our gas exchange is working properly because of math, because we're unable to have a probe and test each alveoli because that would be too painful and too difficult. So we turn to this equation, in order to calculate if our gas exchange is happening properly. And now the next topic we're going to cover is alveolar ventilation, and this is kind of a big topic for this question. The way we define alveolar ventilation is our total pulmonary ventilation subtracted by our tidal volume times our breaths per minute. So our tidal volume is just the volume of our normal breathing, and we multiply it by how many breaths we take per minute. And so that is what we know is our total pulmonary ventilation. When we talk about the alveolar ventilation, we know that there are different kinds of dead space. And so to define dead space, we have anatomical and alveolar. Anatomical dead space is air in larger branches and bronchi and trachea that doesn't reach the alveoli. So this is the air that is unable to get all the way down to the alveoli for gas exchange. The alveolar dead space is the alveolar air that doesn't contribute to gas exchange. So there's air in the alveolus that won't exactly contribute to gas exchange, although this number is very low. This number tells us how healthy the lungs are. If this number is high, then we know that there's a significant problem in the lungs. We know that physiologic dead space here is the addition of anatomical plus alveolar dead space. And so when we refer to physiologic dead space, that's both of them added together. So what I've done is created a little drawing here of an alveolus and the different stages that happen during this alveolar ventilation. And talking about this alveolar ventilation, we'll start here with the alveolar air. This is after inhalation but before exhalation. So what we have is this section here of what we call fresh air. This is the gas exchange that happens after inhalation. We have about 150 milliliters of fresh air here outside of the alveolus. So then when we move over here to exhalation, we see that we've expired 500 milliliters, and so there is 150 milliliters from this dead space and 350 milliliters from old alveolar air. So as the air gets exhaled, this is the distribution of the milliliters of air that gets expired. And so when exhalation happens and we move down to inhalation, we see a different distribution. So in blue, I have the fresh air. So say we have about 500 milliliters inspired, then we have 150 milliliters of what we call old air, and we have 350 milliliters of fresh air. And so then that, in addition, this is our 500 with our additional 150 that is left in the dead space that we talked about before. So this cycle kind of describes the way that the exhalation and inhalation works with the amount of dead space and the ratios of giving the example of 500 milliliters of gas exchange. So now we'll talk a little bit about this table here. This table is really important because it gives us an idea of the different types of breathing and their effectiveness. So here we have 500 milliliters, like we talked about before, is kind of normal breathing. Our normal ventilation rate here, we see this 350 fresh air, which we talked about, and our alveolar ventilation, or how well our ventilation is working, is about 4,200, which we see there. When people are in hypoxic states or nervous states, we have shallow breathing, which is only about 300 milliliters, and the breathing rate will increase to 20 breaths per minute. This 6,000 total pulmonary ventilation stays the same in all three, but we know that we subtract our 150 from our total volume, and we are only left with 150 of fresh air entering each time, so that reduces our alveolar ventilation to 3,000. And the last one, we have 750 milliliters per 8 breaths, which is slow, deep breathing. Again, we have the same 6,000 milliliters per minute, but we have 600 milliliters of fresh air left after we subtracted our 150 from our 750. And so this number, 600 times our breaths per minute, equals 4,800 milliliters per minute of our alveolar ventilation. And so this is why we talk about how if you want to get more oxygen, it's more effective to have deep and slow breaths because our alveolar ventilation is going to work out much better and be much more effective with this type of breathing. So the next thing we're going to talk about are ventilation and perfusion ratios. So this right here, this V over Q is the ratio. V stands for the air that reaches the alveoli, and Q is the blood that reaches the alveoli. So during this ventilation, this is the values of what reaches the alveoli and the blood that reaches the alveoli. And so a normal value is around 0.8, just for reference. So what happens when we have a low ratio are things like bronchitis, asthma, pulmonary edema. And so that causes an airway blockage. Those are things that block the airway. And so that will cause this air that gets to the alveoli to decrease. And so we know that if our numerator decreases, then our total value is going to decrease. So with high VQ, this is opposite. So a pulmonary embolism, which is like a blood clot or something in the lungs, we have a reduced blood flow to the lungs, which means not as much blood is going to get to the alveoli, which will reduce our Q. And when we lower the denominator, then our total value will increase. Similarly, with emphysema, we have stretched alveoli, which causes our Q to go down as well. In the same situation, we will decrease this Q here, which will raise our ventilation perfusion ratio. Lastly, we're going to talk a little bit about COPD, or chronic obstructive pulmonary disease. And so this disease includes both emphysema and bronchitis. So we'll highlight emphysema and talk about that specifically. So emphysema is damage to the alveolar walls, which make them less elastic and enlarged. And so this causes a problem because our lower elastance causes the collapse before all of the air is exhaled. So what we see is that whoever has emphysema is not able to breathe out all of the air that's in their lungs because the reduced elastance does not allow for all that air to escape, because that elastance, that recoil, is what allows our exhalation to work so well. So when that is affected, then we see what's called air trapping right here, which is where we have a big breath in and short labored breaths out. So there are people like smokers or people that have emphysema take big breaths in because they're able to breathe in fine, but it's the exhaling that causes a problem. So they have short labored breaths and they have to use other surrounding muscles or use a lot of effort when exhaling. And so that is what can cause a symptom known as barrel chest, which again highlights extra energy to exhale. And so that can be tiring for people. And so that is the kind of highlight of emphysema and what it does and how it's affected by the damage that it causes and what it's related to.